Before we begin, I highly recommend that you read the introduction to the demo videos series. In this demo 4, I will talk about the logic synthesis of finite state machines and combinational circuits with our tool Syntagate. We will design FSMs from 5 benchmark groups, which I have collected over several years: small, medium, large, huge and super huge. You can download them at synthesa.com. This table contains the parameters of these ASMs. You can find each group of files in benchmark.zip. If you look at the bottom two rows of this table, you may wonder why we are designing such complicated FSMs. And I don't have a good answer for you. But 10 years ago, we didn't think about many things that now seem entirely ordinary. Perhaps in a few years we will want to implement some algorithms in hardware that we can now only implement in software. Or AI algorithms will be so complex that they will require very complicated FSMs to implement them. Or ask Intel why they bought Altera. To design FSM, Syntagate can begin from algorithmic state machine presented with two files, name GSA, two connected lists, and name MIC, list of operators with their microoperations. Or with transition table constructed from ASM. Or with ASMs presented in VHDL or Verilog file. We use the following folder structure for the design in each group. Thus we will design FPGA circuits with the area and delay optimizations and ASIC circuits with gates and matrices. In this video, I will talk about the design of finite state machines and logic circuits for FPGA technology. I will demonstrate the design circuits with gates and matrices in one of our next videos. I won't take the time to demonstrate the design of small and medium-sized projects, as well as huge and super huge. But if this is something you'd like to see, leave a comment in the comment section below. Let's look at the design FSM from the group Large and Real Time. This is the working folder for the design project for group Large, Area Optimization, 6 input LUTs. We will begin from ASMs presented with GSA and MIC files. Here is our small interface to demonstrate logic design with Syntagate. In this interface, I put the working folder in the line project directory and select ASM in the source type, FPGA in the target input, all files to make all designs at the same time, Mealy in the FSM type, one hot encoding. We use two input gates. Our LUT covering algorithm is working better when we begin from two input gates. Area in optimization and 6 in LUT inputs. After that, I must click run, and in about 7 seconds, the runtime is written in file experiment.tim. Syntagate has finished the design of all 6 projects, and we have 14 new files for each project. Let's look at the result of the design of the project Camel. The file Camel T1 contains the transition table of FSM constructed from ASM presented by Camel GSA and Camel MIC. File Camel T12 is the same FSM with one hot state assignment. File Camel V and Camel VHD are Verilog and VHDL files constructed from FSM Camel T1. It is Camel in Verilog, and this is Camel in VHDL. The log file camel test log tells us that no errors were found. To get such information, Syntagate makes the simulation of a constructed circuit, but will return to this a little later. The file camel M96 and camel M97 are of most interest to us. File camel M96 is the netlist of FSM logic circuits with 6 input LUTs. The report of this netlist is presented at the bottom of this file. How do we understand this netlist? For example, let's look at the line 3 or 4. This LUT has 5 inputs. 2 of them are outputs of LUTs 135 and 152. But X22, X29 and X55 are the inputs of FSM camel. And here D70 is the input of the flip-flop number 70 and Y37 is one of the output of FSM camel. Let's talk about the simulation of FSM logic circuit presented in this netlist. For that, Syntagate uses FSM camel T12 constructed from the transition table of FSM camel T1 with 3 additional columns. The second and the fourth columns of this table contains codes of the current at the next state. Instead of using long codes with many zeros and only a single one, here we use codes P/M, where P is the number of the bit equal to 1 in the state vector, and M is the length of the vector. The second last column has input memory function. This FSM has 128 states and 1564 lines. In the process of simulation, Syntagate advances along this table and sends a code of the current state from the second column and the input from the fifth column to the input of the circuit. And the simulation procedure checks that the outputs of the circuit written in the 6th and the 7th columns are equal to 1 and others are equal to 0. Otherwise, Syntagate gives information about a mistake in file camel test log. Thus, for 40th row, the input of the circuit will be all t from 1 till 128 are equal to 0, except t10, which is equal to 1. x11, x12, x45, and x1 are equal to 0. But x41, x13, and x39 are equal to 1. And the output of the circuit should be y3 is equal to y5 is equal to y30 is equal to 31 are equal to 1, and d3 is equal to 1, 2. Our output should be equal to 0. Syntagate can draw the scheme of the netlist, but it is difficult to understand such complicated circuit at the computer screen. But we can look at the part of the circuit selecting some outputs. An example of this subcircuit is shown in this figure. Let's look at the file camel mkh M97. It is the same netlist as in camel M96, but with one additional column. The number of each row in this column is equal to the number of LUTs in the longest path from the input to this LUT. At the bottom of this netlist, we have the list of delays in LUTs for each output of the circuit. the delay of the circuit is equal to 12. To design our project starting with Verilog, we must go to the new folder, large Verilog, and we should put this working folder into the line project directory. Then we must change the source type to FSM and source format to Verilog. In about 7 seconds after I click Run, I will get files similar to our previous design in the working folder. And in the same way, I made a design starting with VHDL. Now let's go to the design with delay optimization. We'll begin from the file FPGA delay, large, and from ASMs. Make only one change, area to delay. We put this working folder to the line of project directory. We should return source type to ASM and I click Run. And we got the design with area optimization. And I will repeat the design with FSMs from group large beginning from Verilog and VHDL. These two figures contain reports constructed by Syntagate for FSM designs from the group large with area and delay optimization. Syntagate can design FSMs with any number of inputs in LUT, up to 99. The experiments with Syntagate can help to predict technological development to determine whether it's reasonable to increase the size of the LUT or not. The results of our experiments with 6, 8, 10 and 12 inputs in LUTs for area and delay optimization are in these two tables. Now let's talk about the design of logic or combinational circuits with FPGA. This table contains the parameters for 4 groups of projects. As in the design of FSMs with FPGA, I won't take the time to demonstrate the design of small, medium and huge projects. It is the working folder Area Optimization 6 input LUTs. We'll begin from logic circuit with M12. This file is a two-level netlist with AND gates and OR gates. It is the circuit in a sum of products form. Its parameters are in the report at the bottom of the file. In interface, we must use working folder for this design. We must change source type logic circuit, FPGA, area, and after that I must click Run. And in about 4 seconds, the runtime is in the file experiment.tim. Syntagate has finished the design of all 5 projects. As a result, we have 7 new files for each project and the report and file report CSV. File name 96 and name 97 are similar to the same files in FSM design. This is the netlist with 6 input LUTs. Its report is at the bottom of this netlist. To design logic circuit with delay optimization, I must replace area by delay in the field optimization. These figures contain reports constructed by Syntagate for designs of logic circuits from group large with area and delay optimization. This table contains the comparison of designs with area and delay optimization. I haven't compared Syntagate with other design tools. However, from 2010 to 2015, comparisons for FPGA design of FSM and logic circuits with 4 input slots were made at several universities. They compared Syntagate with tools of Altera, Xilinx, Mentor Graphics and ABC from Berkeley. In all their comparisons, Syntagate was approximately 30–50% better in area optimization and performed 2 times faster. Moreover, all these tools couldn't design FSMs from the group huge and super huge, and only ABC constructed 2 smallest FSM from group huge. I know only one publication with such comparisons offered by Vegrzen and Karatkevich. Refer to notes in the Demo 4 extended transcript PDF file. I am sure that the companies mentioned have improved logic design with their tools for the latest 5–10 years. Nevertheless, Syntagate suggests a challenge. If a company or university designs all of the FSMs in group huge and super huge within the next month, provided the result is within 5% of Synthesa results, Synthesa will give FSM synthesis algorithms and programs to the successful parties.